Okay, so this course follows on very naturally from Introductory Calculus that you did last term. And in fact, there's some overlapping material, which is quite nice. It gets us going, gets us familiar with the notation and the methods we're going to use. But essentially, we're going to take a lot of the ideas from Introductory Calculus and extend them into multiple dimensions and work in 3D and think about how we can do integrals in 3D, how we can differentiate things in 3D, and how we can develop various theorems that allow us to write down physical laws using some of the approaches that we derive. So we're going to step back and go back to what we did at the end of last term, or in a lot of Introductory Calculus last term, and just think about what it is to write down an integral in the first place, and what we mean when we write down a double integral, and then those ideas will naturally extend when we think about writing down volume integrals. So we're going to start with some nice revision, and we're going to think first of all about multiple integrals in 2 dimensions. All right, so the first thing to ask is, can you hear me at the back? Good. And the other thing to ask is, can you read this at the back? All right, so if it gets small or starts sloping down the page, just let me know and we'll correct that. Okay, so we're going to start by recalling the informal definition of the line integral. So this will be familiar to all of you. So of integrals in 1 dimension. Okay, so it'll all be very familiar to all of you. You've done plenty of examples. So an informal definition of the integral. So the integral, let's say, of some function f of x integrated with respect to x between some definite limits. So we might have x equals a and x equals b. So what do we really mean when we write that down? Well, we can think of that informally as follows. So let's suppose we have some function f which takes values on the interval ab. So ab, on the closed interval ab, f takes these values and returns a real number. So a real valued function. Let's suppose that f is a function. Okay, so we can sketch f. So anything you like. So we have x along here, f of x along here, and we draw some function. Nice continuous function. Okay, and then we can think about what happens when I integrate between x equals a and x equals b. So obviously, when you do that integral, what you're going to return is the area under this curve. So what we do when we think about doing this is we subdivide the interval AB into a number of subintervals. So let's say into m subintervals. We can make them equal length if you like. Doesn't have to be, but let's suppose we do, of equal length. And let's call that delta of x. So delta of x is just a small increment in x. And we let x1, x2, x3, all the way up to xm be points in the integral. Be points in the intervals. Okay, so what we do is we take our domain and we chop it up into intervals. So here we are, and so on. And we make those intervals be of some length delta x. And within the interval, we define some value of x. So in here we have x1, in here we have x2, etc. Okay, and then we can say, so we then have that the integral from a to b of f of x dx is given by the limit as that interval tends to 0. So it's delta x to 0 of the sum of m, or r equals 1 to m of f of x r delta x, provided that the limit exists. So what you're really doing there is you're saying, right, I'm going to take a whole bunch of rectangles. I'm going to do the height of the rectangle will just be the value of the function at that intermediate point in the interval, which we're labeling x1, x2, etc. And I draw those little rectangles and I sum up all those rectangles, take the limit as delta x tends to 0, and that gives me the integral of the function between a and b, provided that that limit exists. So that will always be the case, that the limit will exist provided f is continuous. So this will always be the case provided f is continuous. And we're going to work with well-behaved functions in this course, so we won't have any pathological cases. And you can also think about alternative subdivisions. So I made them all the same. I made them all of width delta x. You don't have to. So alternative subdivisions won't change that limit. Will not change the limit when f is continuous. All right, so that's all very straightforward. You've all seen that. And the reason I wanted to just briefly go over it is because we extend those ideas when we're thinking of integrals in higher dimensions. So now we're going to consider this in 2 dimensions. So we consider a similar approach. When informally defining a double integral. Okay, so let's think about what we're doing now. So let's suppose we consider a region of the plane together with some function. So together with a scalar field now, which we're going to call psi, which will be a function of the coordinates in the plane x, y. Okay, so we're going to have the plane. Here's x, here's y. And we're going to integrate over some region in the plane, which we're going to call R, our region of interest, R. So if I'm thinking of this in terms of its sort of physical interpretation, so if I have x and y now in the plane, and I have my 3rd dimension coming up here, then psi is some scalar field, it's a surface. So here's where I challenge my ability to draw, but something like that. Let's suppose that's psi. And what I want to do is integrate that function over some region in the plane. So here's my R, and I want to integrate that function over that region. So what I'm doing now is computing the volume underneath that surface. So we do exactly the same thing. So this time, instead of partitioning the line into small intervals of width delta x, we partition the plane into small elements of a given area. So we can think about dividing this up into regions and then summing, playing the same trick, summing all the volumes that are given between the surface over that small element in the plane, sum them all up, take the limit, and that will give me the double integral in this case. So we might suppose this has width delta x and height delta y. And we can say, again, we need to define some value of the scalar field. So let's suppose the scalar field psi takes the value, and we're going to call it psi with a subscript I in the center of the ith element. So then on partitioning the plane, region R into smaller and smaller sub-regions. And then taking the limit this time as the region, the area of that region tends to 0. So taking the limit as delta A tends to 0. So I should have said it up here. So I'm going to define delta A to be delta X, delta Y. It's just the area of that little region of width delta X and height delta Y. So then we can define the double integral. So we have that the limit as delta A tends to 0 of the sum. So now I sum over, let's suppose there are n subregions. So I sum from I equals 1 to n the value of this scalar field at the centre of the subregion times delta A, which is the same as saying the limit as delta X, delta Y tends to 0, I equals 1 to n of psi I delta X, delta Y. And we define that to be, so this is definition, the integral over the region R. And to denote the fact we're integrating over an area, not over a single line or single variable, we use a double integral of psi dx dy. And in the last course you did last term, in Introductory Calculus, you've computed a lot of these double integrals. So this is the informal definition of a double integral, and it represents the volume and the integral is the volume under the surface. So again, we have all the usual things. We want to make sure that the limit exists. And it turns out that if psi is piecewise continuous, and R is a suitable region, which covers a lot of sins, a suitable, well-behaved region, there are no difficulties. And in this course, these are the sorts of functions and domains that we'll be considering. Okay, so that's a whistle-stop through how we think about double integrals and how they connect to single integrals. And it's going to be the focus of our lectures in the coming weeks. So these double integrals have a number of properties which are useful to note and exploit. And there's even more in the online lecture notes that you want to take a look at. So the following properties are inherited from integration with respect to one variable. So the properties I'm going to write down are often useful when you're trying to think about careful and more straightforward ways to compute double integrals. So we're going to see examples where it doesn't matter which way I integrate, whether I integrate first with respect to x or then with respect to y or vice versa. But some methods are more advantageous and mean you have to do less work. And these properties can also be exploited to allow you to essentially do less work. So we're going to think about sensible ways to compute these integrals, exploiting various properties. So let's start with the property of linearity. So let's suppose a and b are just constants. So then we have that the integral over r, so some suitable domain in the plane of a times some function of f of x and y plus b times a function g of x and y, all integrated over the plane dA, over the region of interest. Well, that's just the same as a times the integral of f over the region plus b times the integral of g over the region, exactly as you would have seen in integration of one variable. So then we have the property of order. So if we have that a function f of x and y is always greater than or equal to a function g of x and y on the region of interest, so for all x and y in R, then we will have that the integral over the region of f of xy dA will always be greater than or equal to the integral over R of g of x and y dA. All right, and the last one I'm going to write down is the property of domain splitting, which is that sometimes you can exploit the fact it's sensible to split the domain up to make your life easier. So let's suppose that the region R can be written as the union of two regions, so R1 and R2. And the intersection of R1 and R2 is the empty set. So they are distinct and make up the region R. Then the integral over the function over the region R of my function f of xy dx dy equals the integral over R1 of f of xy dx dy plus the integral over R2 f of xy dx dy. And we'll certainly exploit that. Right, so it's very helpful to see examples. And so we're going to start with a nice straightforward example, which is how we integrate some function over a square or rectangular domain. So let's consider R to be the domain spanned by 1, 2 in the x direction and 1, 3 in the y. And we're going to calculate the integral over that region of R, x squared y cubed dx dy. So this is much more simple than probably a lot of the problems you thought about in Introductory Calculus, mainly because the domain is very straightforward. It's just a rectangle. And when domains are rectangles, you don't have to worry so much about being careful about your limits. So I would encourage you, when you're doing these problems, always draw a diagram, so it's clear what domain you're thinking about. So we have x along here and y along here. Then in the x direction, I'm going between 1 and 2. And in the y direction, between 1 and 3. So I'm integrating over some domain that looks something like that. So 1, 2, 1, 3. So a nice straightforward rectangular domain. So when you do these integrations, you've got two choices. You can integrate first with respect to x and then with respect to y, or vice versa, and it makes no difference. But we will see that sometimes it's better to do x first and then y, and sometimes it's better to do y first and x, just depending on the nature of the problem. So we always work from the outside in. So let's suppose first we integrate, sorry, we always work from the inside out. Suppose first we integrate with respect to x, keeping y fixed. So if we're doing that, then what we mean we're doing is we're going to fix y. So we're going to just consider some value of y, let's suppose this one. And we're going to integrate with respect to x. So what we're doing in this, when we do it in this sense, is we split our domain up into lots of slithers that are horizontal, and then we sum them all up. Equally, we could have integrated first with respect to y, keeping x fixed, and when we do that, we split the domain up into slithers that are vertical. But it makes no difference. Okay, so if we integrate first with respect to x, keeping y fixed, so this corresponds to splitting our domain up into horizontal slithers, dividing domain into horizontal slithers. All right, so let's do that. So we're going to integrate first with respect to x. So that means that the integral over my region of x squared y cubed dx dy is just the integral. So integrating with respect to x, my limits go between x equals 1 and x equals 2. My y is between y equals 1 and y equals 3. X squared y cubed dx dy. So keeping the outside integral in play and integrating x squared y cubed with respect to x gives me x cubed y cubed over 3. Now I put in my limits between 1 and 2 dy. Which, if I don't mess up my algebra, I think is the integral from 1 to 3 of 8/3 y cubed minus 1/3 y cubed dy, which is the integral from 1 to 3 of 7/3 y cubed dy. Now I've got a very easy integral to do, just a single integral. So that just becomes 7/3 y to the 4 over 4 between 1 and 3, which is 140 over 3. And the reason this integral was so straightforward to do is because the domain is so simple. The x and the y, if you like, are independent because you're integrating over in a rectangular domain. So alternatively, you could integrate with respect to y and then with respect to x. So with respect to y, then x. So this corresponds to splitting the domain into vertical slithers. Okay. So if we're thinking about what we're doing, so the domain is here somewhere, and what we're doing now is saying, right, I'm going to fix x like that, and then I'm going to split my domain into these vertical slithers and then sum them all up to get my area. So now the integral over r of x squared y cubed, but now with respect to y first, so dy dx. So we change the limits because we switch the order of integration. So now the x is the outer integral, that's appearing here. So that goes between 1 and 2. The y is the inner, so that's between 1 and 3. Now we get x squared y cubed dy dx. And we do the same as before. So we work from the inside out, and we get integrating this integrand with respect to y gives us x squared y 4 over 4 between 1 and 3 dx. Which is, to cut a longer story short, 20 x cubed over 3 between 1 and 2, which is 140 over 3, as expected. So it doesn't matter what order we do things in, we get the same answer as you expect. Okay, you could also do, in this case, to do the integral as follows. So what we could do is acknowledge the fact we're integrating on a rectangle. And then we have the integral over r of the integrand x squared y cubed dx dy. And we can actually split the integrals up, and we could do the x squared dx. So we can do the x squared dx between 1 and 2 times the y cubed dy between 1 and 3. And if I do that, of course, we'll get the same answer. And this is valid because when I'm doing the integrals, so when I integrate 1, 2, 1, 3 of x squared y cubed dy dx, so when I do the integral here with respect to y, I'm holding x fixed. So as far as I'm concerned with this x, it's just some constant, and then I can use linearity to pull it out. So this, when I'm doing the y integral, this x is constant, or held constant, with respect to dy. And so I can just write this as 1, 2. I can pull the x squared out of the y integral, x squared, the integral from 1 to 3 of y cubed dy dx. And then this is just a constant with respect to x. So I play the same game and pull it out. So this is constant. So when I'm doing my x integration, I'm integrating the x squared, but this has just become a number, so I can pull it out. And so I get the integral from 1 to 2 of x squared dx, the integral from 1 to 3 y cubed dy by linearity. So those properties that we covered can be exploited when you're making decisions about how to do your integration. And in fact, if you look at the lecture notes, there's a whole, I think on page 4 of the online lecture notes, there's some further properties that you would expect to see when you do these double integrals, which you can exploit, but it can also be used as sanity checks. So I would encourage you to look at that, because I'm not going to write them down here. It's all in the lecture notes. Right, okay, so it doesn't matter which way we integrate with respect to x or with respect to y. And in fact, we can write that as follows. So given a continuous bounded function so f, which is a function of x, y, given that on a rectangular domain, so we're going to write that as a1, b1 cross with a2, b2. So we're just thinking about functions that are continuous and bounded on a rectangular domain. Then it is the case that the integral from x equals a1, x equals a2, y equals b1, y equals b2 of my function f of xy integrated with respect to y and then with respect to x is equal to the integral from x equals a1, x equals a2, y equals b1 y equals b2 of f of xy. Now doing the x integral first and then the y integral. But this isn't true for all functions f. This is true when f is continuous and bounded. And one of the questions on the example sheet 1, looks at a case where the function, the integrand that you're integrating is continuous, but it's unbounded, and then you'll see that this doesn't hold. Okay. So rectangles are nice and straightforward. As long as we're bounded and continuous, everything's going to behave itself. But of course, we want to do more interesting integrals. We often encounter them in problems we consider. And so for general domains, this is not so straightforward. For general domains that are not simply rectangles, then we have to be much more careful, especially with the limits. So we need to be careful determining the limits of integrals. And it might well be the case, and often is, that it's better to do it one way first and then the other way than the other order of integration. And it may well be some orders of integration are more sensible than others. Okay. All right, so let's think about something a bit more complicated. So now let's consider, so another example. Let's calculate the area of the region R bounded by the parabola y equals root x, the x-axis, and the line y equals x minus 2. Right, so when you're trying to calculate the area, all you're doing is you integrate over the domain of interest, which we're going to draw in a minute. So we'll just call that R dx dy. So that is the area. So you just divide the region of interest R into little area elements, take the limit, sum them up, and that will give you your area of the domain. Right, always draw a diagram. This is where most of the errors come in. A diagram of the region first. Right, so Let's draw the region. So here's the x-axis, here's the y-axis. So the first bounding line of this region is the x-axis. So we can shade the outside of the region. Then we have the line y equals x minus 2, which looks something like this. So that's going to go through the point 2. So there's the outside of that region. And then we have the parabola y equals root x, which is something like this. Oh, it's got a very strange property, this parabola. There we are. So this is the line y equals the square root of x. And so the shading indicates outside the domain. So this is the region of interest that we're trying to find the area of. So this is the R. So as I said, we can integrate with respect to x and then y, or y with respect to x. So we're going to do it both ways and you can decide which you prefer. So 1, let's do the first way. So suppose we first integrate with respect to x. And then with respect to y. So that means that we are dividing this domain into horizontal slithers. So yeah, we're going to fix y and go across this way. So we're going to have a bunch of these slithers that we're just going to take the area of and sum them up. Okay, so we need to now be careful in defining our limits. So if we're integrating first with respect to x, we're keeping y fixed. So x is going to go between whatever value is over here and whatever value is over here. So this one's straightforward. This is just the line, what was it, y equals x minus 2. Yeah. So if I fix y, just treat it now as a number, and rearrange this, I clearly get that x is y plus 2. And so my upper limit for my value of x is y plus 2. Now I go to the other side. So I've currently got y as a function of x, so y is root x. But I can write this as x equals y squared. So the lower limit on my x integration is going to be y squared. So the way to think about this is you're fixing y, it's just become a number, and then you're just asking, well, what values does my x go between? So the lower limit is y squared, and the upper limit is y plus 2. So having defined that, then we end up with the area being the integral. So the lower limit is x is y squared, and the upper limit is y plus 2. But then I have to do a bit more work because I don't yet know what values of y I'm going to pick. So I'm going to go through every sliver, is going to go from here all the way up to here. So as I go up, I'm picking through all those y values that the area is covering. So clearly I'm starting at y equals 0 because I start on this x-axis is the boundary of my domain. But what's this value over here? So what's my maximum value of y? So that's going to occur. To work that out, I have to set y equals root x has to be equal to y equals x minus 2, which is probably easier to say x is equal to y squared, x is equal to y plus 2, and solve that. So y squared equals y plus 2. And so that tells you y is equal to 2 or minus 1, I think, are the solutions of that problem. Now, clearly y is positive because I'm going up into this part of the plane, so I don't want this solution. So this one corresponds to the other solution. If I extend this parabola into the lower half of the plane, where it interacts with this line would be given by y equals minus 1, so we don't want that one. And I also need to know the x value. So when y is 2, then clearly x is 4. So this point of interest up here corresponds to 4 2. So I know that my y limits then go between y equals 0 and y equals 2. So I take all those horizontal slithers and sum the whole lot up. And then I get, what am I integrating? It's just the area, so dx dy. So that just becomes the integral from 0 to 2 of, so now I integrate x with respect to x rather, so it just gives me x. So I get the value of x evaluated at y squared and y plus 2 dy. So that's the integral between 0 and 2 of y plus 2 minus y squared dy. And that's very easy to do, and I won't give all the details. That's just 10/3. So the tricky bit of this one was just thinking about the limits, but the good thing about doing it this way was I only had one calculation to do. So I only had to, once I'd worked out my limits, I can crack on and do it, and I only really had to work out one integration, which was here. By which I mean I didn't have to split up my domain. So let's do it the other way, and I'll illustrate that way, although perfectly viable, turns out to be a bit more work. Okay, so if I do it the other way, so 2. So suppose we first integrate with respect to y, then x. So now let's look at my domain again. So now if I'm holding x fixed, I'm doing vertical slivers. So I start to do this kind of problem. So over here it's straightforward because I'm always going between the y-axis being y equals 0 and whatever value of y I have up here, which is root x, when I'm holding x fixed. But now as I go along, I become over here. Oh, that's a terrible pen. And now my lower limit has changed. Now, it's not that hard. We can certainly do it. But what I'm having to do now is split my domain into 2 parts. So at this point, this is where I can use that property of domain splitting, that the integral over R is the same as the integral over this bit plus the integral over this bit. And the limits on my integrals have changed. So I now have to compute this point here, because this point tells me where I have to change the limits on my integral. And so I hit this x-axis at the value 2, 0. So when I'm thinking about doing my vertical integration and then summing them in the x direction, I have to split my x values up. Okay, so if x is between 0 and 2, then y goes between 0 and the upper limit, which is root x. So provided I'm over here, the lower limit will be 0 and the upper limit will be root x. Now, if x goes between 2, then y goes between, so now the lower limit becomes x minus 2 and the upper limit is still root x. So now the area is the integral. So the first integral I do, so integrating with respect to y first, so I'm going to consider x between 0 and 2, and then my lower limit is 0 and my upper limit is root x for the y integration. And then I have to add to that the other bit, where now my lower limit is x minus 2 and my upper limit is root x dy dx. Okay, so this particular example, I mean, it's fine. You can do these 2 integrals. It won't take very long. But there is an additional step to doing it this way. So if you work all that through, and I won't do all the detail, you'll get the answer 10/3 as you'd expect. So in this example, it is simpler to do the x integration first. Okay, so what we've done today is we've thought about integrating over simple regions, which are just rectangular, where everything, provided f is well behaved, everything is well behaved. And we thought about how to think about more complex domains, where you now need to think about the order of integration. Often we think about integrating over domains, so sometimes the domains are circular or they have a particular geometry, where it's more appropriate to actually use a different coordinate system altogether. And you'll have seen already how you can, instead of integrating over Cartesian coordinates, you could use, for example, polar coordinates. And so what we're going to do in the next lecture is think about more complex domains where making a change of coordinate system and exploiting the Jacobian actually makes your integration step a lot easier. So we'll stop there, and tomorrow I'll pick that up.